Hello, students. It's quite an honor to make a series of lectures recorded and provided to you. With this opportunity, I would like to explain about the introduction to crystallography. Here, basically, I wanted to start from how to derive the 7 crystal systems and 14 Brava lattices and 32 point groups. I may not go to the derivation of 230 space groups, but that's basically the purpose of these lectures. But in order to understand the crystallography of materials, we have to understand the stereographic projection, because this stereographic projection is one method to understand the futures which is in 3 dimensions to 2-dimensional scales. So stereographic projection is one method for representing 3D space as a 2-dimensional drawings. It provides an alternative way for performing crystallographic calculations to analytical algebra, and is useful in visualizing the interrelationship between various crystal planes and directions. Well, there are a few of the stories about the derivation of this stereographic projection, but anyway, this stereographic projection was first applied to crystallography of materials in the work of Newman and was further developed by Miller. So let's think about this. Now we have some interesting features which is in space. Now we would like to understand the relationship between all the planes and the directions of this feature. So what we will do is we first draw a sphere in here and put the objects that is interesting to us as a tiny small objects, and put those objects in the center of the sphere. Okay. Now, what we will do is we designate the plane as the pole. The planes be represented by a set of plane normals radiating from some one point within the crystal, which we call poles. And this pole represent planes. What it means is, if we designate 100 planes in here, then you draw the normal lines to this plane, and these normal lines finally touch the surface of the sphere, and this one point is basically designate the 100 planes of these crystal structures. And if you draw 010 planes, then you draw the normal lines to that planes, then these emanating lines will touch the surface of the sphere at this point, and this is designated as one point, and which represents the planes. In this case, of course, this is 010 planes. And if you have 001 plane, again the same thing. You draw the normal lines to the planes, and this line touches the surface of the sphere, and it represents as one point, and this is what we call 001 plane. So plane is now designated as a point in the surface of the sphere, which is what we call stereograms. And again, if you draw 1 bar 00 planes, then 1 bar 00 plane can be designated as a pole in here, and 01 bar 0 plane can be designated as a pole in here, and by the same token, 001 bar plane is designated as the pole. And certainly, by using the vector theorem, you know that you can measure the angle between any 2 vectors, which is in here A vector and B vector. And now these 2 directions, the angle between these 2 directions is designated by cosine theta equal A dot B vector divided by the magnitude of A vector and B vectors. Okay, so in here I designated basically 100 group poles of a cubic crystal. Now that plane can also be represented as the lines which lie in the planes, and these lines can be extended, and you can find out the set of point which represents these directions. For instance, now let's say if I'm interested in this plane, okay, now you can designate by two different ways. One is you draw the normal lines to the plane, and these normal lines touch the surface of the sphere as the P2 point. So this point designates this plane as the pole. Okay, and by the same token, if you draw any lines in that planes, okay, there are many set of lines which lies in the plane. You draw the extension of these planes and find out the group of the point which touches the surface of the sphere, and then these lines can also designate the planes of this particular plane. Okay, so plane can be represented by the pole, which is the perpendicular to that directions, and plane also can be represented by the set of directions which lies in the plane. Now let's think about another one more planes, which is in here in this plane. Again, you draw the normal lines to the plane, then the line touches the surface of the sphere at the P1 point. So P1 point also designate the plane as a pole. And by the same token, you draw all the lines in the plane and extend it and find out the set of points which touches the surface of the sphere. Then of course this line group of points also designate that planes. So there are two different ways to define the plane as a pole or the set of lines which is in the planes and extended it, and you can find out the set of points which touches the surface of the sphere. And here, of course, you can find out the angle between this P1 plane and P2 plane by these angles, but also you can define the angle between these two poles by the angles between this P1 point and P2 point. Okay, but in this case, of course, there is one critical assumption that these two planes should pass through the center of the sphere. Okay, so planes be represented by the trace which the extended plane makes in the surface of the sphere. And when the plane passes through the center of the sphere, it will intersect the sphere in a great circle, which is this circle is the great circle which we can make with the same radius sphere. Okay, so you imagine the sphere and you imagine cut the sphere through the center of this sphere, then you can find out that makes the great circle from these spheres. And when you do that, you can measure the angle between two planes. The angle between two planes can be measured. There are great circles, angles in the great circles, and the angle between their normals. So this is still, we have three-dimensional objects in the center of the sphere. Now you designate the planes by two different ways, but still your representation is on the surface of the sphere, so still it is in three-dimensional objects. But what we try to do is we try to deliver this information to two-dimensional planes, from three-dimensional information to two-dimensional informations. So what we do is, this is basically stereographic projection. So far I explained about stereograms, which is in three-dimensional space, which is on the surface of the sphere. Now we try to move this information to the two-dimensional planes. So what we do is this. So far, let's say, assume that we have pole P, which represents this C plane in the center of the sphere. Then if this pole is on the other half of the sphere, basically you can draw the big circle, which is the equatorial planes. And if this pole is the other side of these equatorial planes, then you designate one point which it touches on the other side of the sphere, and you extend these lines, poles, to these planes which is basically touches these spheres. Then this P plane is now is represented as P prime in this case. So this plane is basically now representing stereographic projection planes. Okay? In this way, you can designate all the information in the surface of the sphere to two-dimensional space. But if any information is the other side of these equatorial planes, then if you extend it, then it goes to the infinite. So we cannot do it. So in this case, we move these planes on the other side of this B point, touches this B point. Now I'm looking at from this A point and projected it, and now we can represent on the surface of these planes. So this information is now what we call stereographic projection. And in doing this way, for instance, if you extend it, then this equatorial plane can be represented as one big circle, and any information on the surface of this sphere is now can be represented on the surface of the planes. So the lattice plane in a crystal is represented as a C by its normal CP as a pole. This normal CP is represented by its pole P. Now the pole P is represented by its projection to P prime. Now this projection is two-dimensional planes. So if we draw all the information on three-dimensional sphere, then this is a stereogram. And now we move this information to two-dimensional plane, then this is the projection. Okay? So this is what we call stereographic projections.